Hello, everybody, and welcome to another wonderful day of physical chemistry. So over the last couple of lectures, we built up an idea of how we can talk about combining electrons to form a general electronic structure around an atomic system. So we can use our orbital approximation to combine orbitals. We can use Z effective on our electron shielding to describe how favorable any orbital is. But what we haven't figured out is a way to figure out which electronic combinations are possible. Can all my electrons exist in the 1s orbital? Do they have to spread out? And unfortunately, in order to do this, we need a little bit more quantum mechanics, and we need to figure out when electrons can exist in the same location or not. And in order to do this, we're going to essentially need another set of principles. So what we're going to make use of is the Pauli exclusion principle. So you probably heard this in Gen Chem. It's the idea that no more than 2 electrons can occupy the same orbital at any given time. This is the classic reason why electrons exist in pairs in orbitals. So most of you know why this happens. Not everyone knows why. So in order to explain this phenomenon, we actually need to bring in our fourth and final quantum number, spin. So spin is kind of an odd one to try and think about. And a good way to try and examine how it came about is to figure out historically where it originated. So what was originally happening is back in the 1930s, some physicists were shooting silver atoms at a metal wall through a magnetic field, as one does. And what they found was a very interesting effect. And when they shot the silver atoms through the electronic field, not a single electron ended up straight on from the emitter. Not a single one. And we would expect a nice even distribution of silver atoms all around the screen. Instead, they ended up in 2 discrete locations. One up, one down, equal amounts up as down. All right, and this is a little bit odd, as it shows that it turns out silver is magnetic. Silver shouldn't be magnetic, because one of the important things to think about is most of the magnetism is going to come from angular momentum. But look at the electronic configuration of silver. So in the core electrons, all the electrons will have equal amounts of positive and negative orbital angular momentum. And it's got a full d shell. So there's no net orbital angular momentum for the d shell either. And s orbitals, by definition, also have no net angular momentum because they have an L of 0 and an M sub L of 0. They shouldn't respond to a magnetic field. And it turns out the only good explanation for why this happens is if we say that it turns out the electrons themselves have a magnetic field. And this can be explained if I say that the electrons have a net spin of 1/2. And so one way you can think about this is I have an electron. It is a charged particle. And it turns out that moving charged particles generate magnetic fields, as we've talked about before. So normally we think about the electron circling around the nuclei, use our right-hand rule, we can use it to figure out the angular momentum and thus the magnetic field. But it turns out that they don't have to just orbit. You can imagine if the electron's kind of like a softball and I throw it and it starts spinning. Well, that spinning of the electron itself will actually generate a magnetic field. And depending on the direction of which it spins, throw it, say, right-handed or left-handed, will give me a spin either pointing up or down. 2 major directions it can spin, clockwise, counterclockwise, and this should give us a M sub s. So this, again, will tell us how much of the angular momentum is pointing in the z direction. Now, one of the cool features is we've already talked about angular momentum, and orbital angular momentum is going to behave almost exactly like spin angular momentum. So I can use all my equations from a rotating system before, and I can find the total angular momentum for my spinning object is going to be, which will often be denoted as an uppercase S, which I'm sorry, is going to be distinct from our lowercase s. So the uppercase S is going to be our spin angular momentum. So total spin angular momentum, classic angular momentum units, joules per second. The lowercase s is again our quantum number, which, as we said, is always 1/2. It's always got a half order spin. So we can go ahead and plug in that equation. So it's just going to be 1/2 times 3/2 times h bar, which when we plug it all in ends up being about 0.87 h bar, or around 9 times 10 to the negative 35 joules per joule seconds. So not exactly a lot of angular momentum, especially if you think about how much was being generated by, say, our by our orbital angular momentum, which tended to have spins of 1 and was thus a larger orbital angular momentum, even if it was in the p orbital. Now, this gives us the total orbital angular momentum, but it turns out that all of our orbital angular momentum, we don't know what direction that's pointed in. So we have to figure out what the possible values are. And so we can use the same antics we did for Jz, but now instead of Jz for total angular momentum, I'm going to use an uppercase S, where this is going to denote the spin angular momentum in the z direction. But it uses the same equations, h bar times the quantum number, which in this case is now m sub s. So again, this can be pointed up or down. So it has 1/2 h bar plus or minus. Now, one of the things that I do kind of like pointing out here is that I can have up to 1/2 h bar angular momentum pointed up or down, but I know the total system has about 0.87. Where's the missing 0.37? Well, it turns out for that we have to revisit our old friend Heisenberg. And if you remember, the Jx and Jy operators don't commute, which means the same thing holds for spin. So I know that most of my angular momentum will be pointed up or down, say with or against the magnetic field, but a little bit of it is going to be pointed in the other directions. And it turns out we really can't determine how much. Now, most of you are probably starting to wonder, where the heck do we get this 1/2 value from? Well, it turns out that this mostly comes from quantum. A, it matches up with experimental data, and B, it also matches a lot of quantum mechanics. So quantum mechanics actually has a special name for objects that have half integer spins. So 1/2, 3/2, 5/2. And these particles are called fermions. And it turns out that fermions have a really cool and very unique property. It turns out they can't occupy the exact same quantum state. So this means that if I have two objects or two electrons with the exact same spin, then this means they have to, say, occupy different orbitals. So their L has to be different, their M sub has to be different. They have to occupy a different physical space. And as a result, because they can't occupy the same space, they often have to work around each other, expand, interact, and turns out that this means that they constitute many of the building blocks of nature. So it turns out pretty much most of the elementary particles you're familiar with are going to be fermions. So this includes neutrons, protons, electrons. So this is the reason why we have a nucleus and not a point particle at the center of an atom, because neutrons and protons can't occupy the exact same space. Similarly, this is one of the reasons why all of our electrons don't just condense down to the 1s orbital, because they can't all occupy the same space. I can only let 2 electrons sit in the 1s orbital. Otherwise, get out of town, you have to find somewhere else to be. Now, it is worth noting that not all particles have a half spin. Turns out some particles have a full spin. So this means they have a full h bar of angular momentum. These particles are called bosons. So you can think about these as particles that say don't spin at all. So they can just stay stationary. They don't have to spin to exist. But if they do spin, they can say spin with a full h bar of angular momentum, or 2h bar, or 3h bar. Now, turns out that bosons actually are allowed to occupy the exact same space. So I can put 2 or 3 or 4 bosons in the same physical location and no problem. And it turns out we've already encountered one famous boson, and no, we have not dealt with the Higgs because that deals with gravity. And that is the photon. And one of the cool things about bosons, whether it's the photon or the Higgs, is typically what they do is they transmit energy and forces in between fermions. So since fermions can't exist in the same physical space, in order to transmit energy in between the two of them, in between each other, they have to interact through some sort of field or through some sort of particle. And this is typically where fermions come into place. So one electron can lose energy and emit a photon, and then that photon can be absorbed by another electron and then increase in energy. But the energy transmission typically occurs through photons. And the reason why people talk about the Higgs bosons is it does a similar thing, except for with gravitational energy instead of electromagnetic energy. But one of the reasons why it's so important that photons are indeed bosons is because this is exactly how a laser works. A laser essentially constitutes stacking a whole bunch of photons right on top of each other with the exact same wavelength, which means they've got the exact same wave function. But since they've got the same exact wave function, this means all I'm doing is increasing the amplitude, and I get a net wave function with a gigantic single amplitude. This is more or less how a laser is able to transmit so much energy. So we're going to be mostly spending our time talking about fermions. We love our good electron, but it's worth noting that if I'm going to interact with a photon, it too is going to include a little bit of angular momentum, which is going to come into play much later. However, next time, we're going to dive a little bit more into the Pauli principle and some of the implications of the fact that electrons are fermions. So we're going to figure out how they get out the way. Till next time, take care.